Welcome to Career Guidance Max playlist. In this video, I'm going to start type 4 symmetric matrices with repeated eigenvalues. This one is very important. So after this type 4, we are going to start a reduction of quadratic form into canonical form by orthogonal transformation. Most probably, while solving in orthogonal transformation, we are going to apply type 4. It's repeated there itself, so you can listen very carefully. This one also important. Here I taken one symmetric matrices. See how to find symmetric matrices. A equal to n transpose. When you are changing row into column, column into row, the matrix will not change, same it will remain. So it is a symmetric matrices. Next we have to find eigenvalues, whether it is repeated or not. We'll check it. Okay, the given matrix I'm taking A, that is 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3. So which is 3 by 3 matrix. So we have to form a characteristic equation also based on 3 by 3 matrix. So that is I'm going to write lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. Is this our general characteristic equation for 3 by 3? From this I'm going to find s1. s1 equal to, I'm writing trace of A is nothing but trace of A means sum of the diagonal element of the given matrix. 6 3 3. We can add 6 plus 3 plus 3. You will get s1 equal to 12. Right off. Next I'm going to find s2. So s2 equal to sum of minus of main diagonal elements. Based on diagonal elements, we have to find minor values. So here diagonal elements are 6. Based on 6 means omit this row, this column. Remaining you can write in some determination form 3 minus 1 minus 1 3. 3 minus 1 minus 1 3. Okay, and plus take second diagonal element 3. This row, this column omit 6 2 2 3. Write in determinant form. And third diagonal element 3, so omit row and column. Remaining I will write 6 minus 2 minus 2 3. And now simplify this. 3 into 3 9 minus 1 and plus here 18 and minus 4 plus 6 into 3 18 and minus 4. So simplify this. 8 plus 14 plus 14. You will get s2 is equal to 36. So now I am going to find s3. s3 is nothing but a determination of A. So I am going to write determination of A matrix. 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3. Okay, so apply determination rule. 6 of 3 into 3 9 minus 1 and minus of minus 2, the formula, the column. Minus 2 into 3 minus 6, 2 minus 1 minus 2 plus 2 and plus 2 of these two, column and row. Minus 2 minus 1 plus 2, 2 into 3 6 minus 6. So simplify this. 6 into 8 minus into minus plus 2 and minus 6 plus 4 minus 4 plus 2 into 2 minus 6 minus 4. So I'm writing 6 into 8 48 minus 8 and again minus 8. So I will get s3 equal to 32. So after finding s1, s2, s3, now I am going to write the characteristic equation. The characteristic equation is lambda cube minus S1. S1 is 12 into lambda plus S2 is 36 into lambda and minus S3. S3 is here 32. So equal to 0. Okay. So this is our new characteristic equation. So now I am going to find eigenvalues. So this characteristic equation is cubic model. So we have to apply synthetic division. So the synthetic division, I am going to write coefficients of all lambda values. Lambda cube coefficient is 1 and lambda square coefficient is minus 12. Lambda coefficient is 36 and finally I am writing constant minus 32. So here we have to apply 1, minus 1, 2, minus 2 like that. 1 and minus 1 not possible because here it is a big number. So I am going to try 2. So 1 plus 0, 0. 2 into 0, sorry, 1 plus 0 is 1. 2 into 1, 2. Minus 12 plus 2, minus 10. 2 into minus 10, minus 20. 36 minus 20, 16. 2 into 16, 32. Minus 32 plus 32, it is 0. So that here I am writing 1 root is lambda 2. This one I am writing as a quadratic form. 1 is lambda square minus 10 into this one lambda and constant plus 16 is equal to 0. The 16 constant I will take. Which two number multiplication gives 16? 2 and 8. When multiply these two, you will get 16. And when I am adding these two also, we need to get minus 10. But here minus 10, here plus 10. So you can put here minus minus. When I add these two, you will get minus 10. When multiply these two, you will get plus 16. So that I will write in a linear factor lambda minus 2 and lambda minus 8 is equal to 0. So equating to 0, you will get lambda equal to 2 and lambda equal to 8. So therefore, the eigenvalues are lambda equal to 2, 2 and 8. So the given matrix is symmetric and eigenvalues also repeated. Okay, keep it in your mind. This is very important. Next I am going to find eigenvector. The formula is a minus lambda I into capital X equal to 0. So here A is given matrix. I am going to write 6 minus 2 and plus 2 minus 2 3 minus 1 2 minus 1 3. Okay, and minus lambda into I matrix, identity matrix 3 by 3 because of given matrix 3 by 3. So we take an identity matrix also 3 by 3. A capital X we can write x1, x2, x3, 3 variable. And 6 minus 2, 2 minus 2, 3 minus 1, 2 minus 1, 3. As it is you can write. And multiply second matrix with lambda. I will get lambda 0, 0, 0, lambda 0, 0, 0, lambda into x1, x2, x3 equal to 0. So now you can subtract both the matrices. 6 minus lambda and minus 2 minus 0 minus 2, 2 minus 0 2, minus 2 0 minus 2, 3 minus lambda, minus 1 0 minus 1, 2 minus 0 2, minus 1 0 minus 1, 3 minus lambda into x1, x2, x3 is equal to 0. Now row wise, column wise you can multiply, you will get the equation 6 minus lambda into x1 minus 2 into x2 plus 2 into x3 is equal to 0. Next one, minus 2 into x1 plus 3 minus lambda into x2 minus 1 into x3 equal to 0. And third row, 2 into x1 minus 1 into x2 plus 3 minus lambda into x3, which is our general equation of I. From this general equation I, we have to substitute our eigenvalues. Always we have to substitute first non-repeated eigenvalue, then we can substitute repeated eigenvalue. Okay. So case 1, I am going to substitute first non-repeated eigenvalue, that is lambda equal to 8 in the general equation of I. Okay. Substitute here lambda equal to 8. 6 minus 8, I will get minus 2x1 minus 2x2 and plus 2x3 is equal to 0, which is equation number 1. In second equation, I will apply lambda is equal to 8 minus 2x1 minus 5x2 minus x3 is equal to 0, which is equation number 2. Next you can substitute here third equation lambda equal to 8 minus 5, again you will get, so 2x1 minus x2 minus 5x3 equal to 0, which is equation number 3. So when substituting lambda equal to 8, we will get 3 different system of linear equation. So we can able to apply cross-road method. From this, take any 2 equation. I will take equation 1 and 2. By cross-rule method, x1, x2 and x3. Take equation 1 and 2. First I am going to find x1, so omit x1 coefficient, remaining you can write in determinant form. So minus 2 plus 2 minus 5 minus 1. Okay. Next I am going to find x2, so omit x2 coefficient both the equations, and remaining you can write determinant form. We can write first always x3 coefficient 2 minus 1, next x1 coefficient minus 2 minus 2, and x3 coefficient omit, remaining you can write determinant form minus 2 minus 2 minus 2 minus 5. So simplify this, x1 divided by minus 2 into minus 1 plus 2 and minus 5 into 2 minus 10, formula minus, so plus 10 equal to x2 divided by 2 into minus 2 minus 4, and this is 2 minus 2, and here x3 divided by minus 2 into minus 5 plus 10, and this is minus 4. So we'll get x1 divided by 12, x2 divided by minus 6, and x3 divided by 6 plus 6, 10 minus 4. Now you can commonly divide by 6, you will get x1 divided by 2 and x2 divided by minus 1 and x3 divided by plus 1. So this is our first eigenvector. I am going to write capital X1 is equal to 2 minus 1 plus 1. Okay, this is our first eigenvector. When substituting non-repeated eigenvalue lambda equal to 8, we will get the eigenvector x1 equal to 2 minus 1, 1. So next I'm going to find eigenvector of 2, that is I'm going to substitute the repeated eigenvalue of lambda equal to 2 in our general equation I. Okay, so here you can substitute lambda equal to 2, 6 minus 2, I'll get 4x1 minus 2x2 plus 2x3 is equal to 0, which is equation number 4. Next here you can substitute lambda equal to 2, 3 minus 2, 1. You will get minus 2x1 plus x2, and next minus x3 equal to 0, which is equation number 5. And here you can substitute lambda equal to 2, 3 minus 2, 1. Again you will get 2x1 minus x2 and plus x3 equal to 0. This is our equation 6. When substituting lambda equal to repeated eigenvalue, I will get this system of linear equations. We have to check whether it is same or different. From equation 4, I will take 2 outside. I will get 2x1 minus x2 and plus x3 equal to 0. From equation 5, I will take minus outside. That means 2x1 minus x2 plus x3 equal to 0. And sixth equation, 2x1 minus x2 plus x3 equal to 0. That means all the three equations are same. So we cannot able to apply cross rule method. Simply you can take one equation from this. I'll take first one, 4x1 minus 2x2 plus 2x3 is equal to 0. Okay, so usually when we take an repeated eigenvalue, your equations also same, means one eigenvector you can find based on put x1 equal to 0. Here I am going to put x1 equal to 0. Okay, I will get minus 2x2 plus 2x3 equal to 0. Shift to right hand side, you will get 2x2 equal to 2x3. Right off, both sides will cancel 2, you will get x2 and x3. That is understood. We can write x2 divided by 1, x3 divided by 1. Right off. Then now I am writing the eigenvector. x2 is equal to, already we know x1 equal to 0. So x1 equal to 0 and x2 1, x3 1, which is our second eigenvector. So we have to find third eigenvector. Usually we are applying, while finding third eigenvector, I will take x2 equal to 0, we will get a third eigenvector. But here we cannot do like that because this is symmetric and repeated eigenvalue. So here we have to use one new concept while finding eigenvector of 3. So while finding eigenvector of 3, we have to consider here capital X3 equal to L, M, N as an eigenvector because of symmetric matrices and repeated eigenvalue, means third one we have to follow this model while finding eigenvector. So the given matrix is symmetric matrix. So I'm going to write this x3 is orthogonal to x1 and x2 eigenvector. Okay, so this x3 is orthogonal to x1 and x2 eigenvector. Now usually orthogonal definition is x into y is equal to 0. Already you know that if you are applying 2 vector, when multiplying this 2 vector, if it gives 0 means which is orthogonal. X is perpendicular to y, y is perpendicular to x, like that we can assume. In that similar manner, here I am writing x3 is orthogonal to x1 and x2 means I will write the formula x1 transpose into x3 equal to 0. That is I am going to write here x1 transpose into x3 equal to 0. And second formula x2 transpose into x3 equal to 0. x1 and x3 are orthogonal and x2 and x3 are orthogonal, like that. Here we know eigenvector of x1 is equal to 2 minus 1 1 and x2 eigenvector is 0 1 1. I'll write x1 transpose means 2 minus 1 1. I'm writing row wise 2 minus 1 1. Okay, and what is x3? We considered L M N is equal to 0, which is gives the equation 2L minus M plus N is equal to 0, which is equation number 7. And x2 transpose into x3. I'll write x2 in row wise 0 1 1. Already we know x3 is L M N is equal to 0 by orthogonal. So now we can write as a equation form 0 into L plus M plus N is equal to 0, which is equation number 8. Now this equation 7 and 8 are different. I'm going to substitute cross rule method. So from equation 7 and 8, I'm applying cross rule method. So here find L, M and N. If you want to find L from this both the equation, you can omit the coefficient of L. Remaining M and coefficient you can write in determinant form. That is, I'm writing minus 1 plus 1. Second equation, 8th equation 1 1. Okay. Next I'm going to find M. That means from the both the equations you can omit M coefficient. Remaining you can write in a determinant form. First always you can write N coefficient. Similarly x2 finding model. N coefficient 1 1. Here L coefficient 2. Here 0. And N. Omit N coefficient. Remaining you can write in determinant form. 2 minus 1 0 plus 1. Now we can simplify this. Minus 1 into 1 minus 1 1 1 plus 1 minus 1 is equal to M divided by 1 into 0 1 into 2 2 minus 2. Cross multiply, and 2 into 1 2 and this is 0. So that I'll write here L divided by minus 2 and M divided by minus 2 and N divided by 2. Okay, so commonly I'm going to divide by minus 2. So I'll get L divided by plus 1 and M divided by plus 1 and N divided by minus 1. So therefore the eigenvector x3 equal to LMN, that is the answer 1 1 minus 1. This is our final answer. So while doing problem in symmetric matrices with repeated eigenvalue means, that case I means eigenvector of x3 we have to find this model. We have to consider x3 equal to LMN and this x3 is orthogonal to eigenvector of x1 and x2. So that based on this you will get what is LMN, the similar process. Okay, suppose in these symmetric matrices and repeated eigenvalues, all the three eigenvalues are same. Symmetric matrices and repeated eigenvalues, all the three eigenvalues are same. For example 2 2 2. So how to find eigenvector? Symmetric matrices with a repeated eigenvalue. That means first you can substitute this 2 in your eigenvector equation. You will get different three equations means no issues. We can able to find put cross rule method. You will get equation cross rule method. You will get eigenvector of 2, then which is equivalent to remaining 2, and find third eigenvector in the form of LMN. Suppose all the three equations are same means find one eigenvector based on put x1 equal to 0. You will get capital X1 eigenvector. Again put small x2 equal to 0, you will get capital x2 eigenvector. Then you can find eigenvector of 3 based on consider x3 equal to Lmn, and this one is orthogonal to x1 and x2, and find the value of Lmn, that is our eigenvector of 3. Okay, that's it pa. Up to this we completed all 4 types of models, how to find eigenvalues and eigenvector. So based on this, we are going to start in next video orthogonal transformation. So we are going to reduce the quadratic form into canonical form by based on orthogonal transformation. So here we solved in every type one problem. Remaining problem you can practice more. Okay, definitely you can able to find eigenvalues and eigenvector. Then when you can able to attend 16 mark orthogonal transformation. Okay, thank you pa.